Hi, my name is Anaya and I'm in grade 9 from Fairview School. I am here to present my science fair project, Particle Accelerators, the Future of Physics. We have so many mysteries yet to be discovered about our universe. We are studying galaxies and orbits of planets, and we just sent a rover to Mars. We are discovering all these new, huge planets, galaxies, nebulas. But we still don't know very much about our universe. And even more than that, we don't know much about the opposite way. Smaller things. Not as small as the atomic level, even smaller. Smaller than even the subatomic level. This is where we get introduced to the quantum scale. Now, my project is about particle accelerators, but I will briefly first explain the fundamental basics that we need to understand how particle accelerators work and how they really function to make these particles accelerate. I will describe it very briefly, but if you would like to know more in more depth, I have my report and my research that you could go ahead and read. So do you see this table? To me, it looks a lot like the periodic table of elements, and it's very similar because this is a standard model of fundamental particles, while the periodic table of elements is the model of elements. This table, you can see 4 different colors: purple, green, brown, and yellow. The purple particles are called quarks. Now these are quarks, they're very fundamental, and they make up other particles. Protons and neutrons are not on this chart because they are not fundamental. They are made up of quarks. Quarks have different flavors and different types. Then we bring ourselves to the leptons. If you see this chart, you can see leptons here. Leptons are again fundamental, and they are not affected by a specific force called the strong force. Then we have the brown. These are the force carriers. Ever since we've been little, we've been taught that forces are like this invisible repulsion or attraction that causes some movement or change in our environment. But as we get older, we understand that force is really just a particle, an exchange of a particle that creates the effect of a force. There are 4 fundamental forces: the gravitational force, electromagnetic force, the weak force, and the strong force. Now, as I said again, leptons are not affected by the strong force, while hadrons, the other part of subatomic particles, are affected by the strong force. So these brown particles are the force carriers. They are the particles that are exchanged to create the effect of the force. So these force carriers are special because they are the force. So as you can see in this picture, they're gluons, or the strong force that keeps the quarks inside a hadron together. So hadrons are split into 2 more sections: baryons and mesons. The main difference is baryons are made of 3 quarks, while mesons are made of 2, specifically a quark and an antiquark pair. Again, mesons are also called bosons sometimes, which follow different statistics than fermions or baryons. So this is the subatomic particles. There's leptons, hadrons, and hadrons are split into more different fundamental parts. Then we have, on this chart, we have other particles, antiparticles, neutrinos, and if you would like to learn more about them, you can go and read my report and my research, and there is more description detail about them. But antiparticles are basically particles that have opposite charge, and then neutrinos are almost called ghost particles because they can travel through light years of dense material without being detected. So then, now do you see this? Right before we jump to particle accelerators, let me quickly explain this. This is a quantum field. Every particle on here has its own respective quantum field. Now, let's take an example. Let's pretend that this is the electromagnetic quantum field. Its corresponding particle is the photon. Now let's say that there is no photon in a specific field. These fields are always there. Whether the particle is there or not, the fields are fundamental. They will always be there. In this space, all the fields are there. Now, the field has a value of 0 because there are no current photons in the field. Then you take 1 photon and send it. You see this orange highlighted path? Let's pretend that 1 photon is traveling that path. The values of the field where the photon is will change. and it will get higher because it's one photon, it'll be one. And so as you know, quantum fields are a field respective to its particle, and when the particle's energy enters its respective field, then you will get a change in value or a change in energy levels in that part of the field. So again, now that we know fundamental basics, if you want to know deeper, again, there's my report and research. Let's move on to particle accelerators. The LHC, Large Hadron Collider, located in Geneva, Switzerland, invented by the company CERN, is the largest particle accelerator in the world. Particle accelerators are commonly used in TV shows, movies. They're very popular in giving superheroes powers, but they are nothing less than a superpower to scientists. Particle accelerators, basically what they do is they take protons and neutrons, there's no electrons, and they accelerate them at such incredible speeds and collide them. So this is a quick diagram of the LHC. I drew all these pictures here. So this is a quick diagram of the LHC. The protons and neutrons are sent in. Actually, the atoms are sent in. And as they go through, the electrons get stripped away from its atom. And for these first three particle accelerators, the purple, the green, and the blue, the particles are really just gaining speed. Then when they hit the orange particle accelerator, the real Large Hadron Collider, from the SPS, they are sent in two different directions. And they go and they collide. Now there's 4 different particle detectors here, CMS, ALICE, ATLAS, and LACB. But that is, again, explained more in detail. Now, how do particle accelerators actually create new particles? This great man, Albert Einstein, came up with an equation, the most famous equation in the world. E equals mc squared. This equation means that energy and mass are interchangeable, or energy and mass are 2 versions of the same thing. Now, I really want to stress how much energy a particle accelerator contains when it's running with the collisions. There is extreme amounts of energy in there, enough to create bombs, and it's crazy amount of energy. Now, what happens is when these particles collide, they create disruptions. What would you expect to happen? Let's say you take 2 protons and collide them. What would happen? Well, I would expect a bunch of quarks to fly everywhere, maybe the gluons that keep the quarks together. But what happens is because there is so much energy created, and the collisions actually disturb the field, so the fields can actually interact with each other during the collisions. The fields combine, the particles combine, and there's so much energy, and since energy is equivalent to mass, you guessed it right, we get a new particle. But for that, you need the right speed, the right frequency to create these huge, huge particles. The last particle I didn't talk about, the Higgs boson. This is a boson, also known as a meson, but it has its own field, and it was literally discovered at the LHC in CERN. And it was a big news, but it was such a high speed that these particles were moving at. All the energy combined created this massive, massive particle. It's the second heaviest particle after the top quark on this standard model. So particle accelerators don't just give us new discoveries, new scientific knowledge, new fields and forces. They're used for so many other things too. Particle accelerators are used in medicine. Believe it or not, 70% of particle accelerators in the world are actually located in hospitals. Well, what do particle accelerators do in hospitals? They're used for creating so many PET tracers or CT scan tracers. They are used for creating hydrogels, which are layering or coating. Last year, my science fair project was on nanotechnology, and I studied femtosecond optical laser surgeries. But now I'm doing particle accelerators, and I realize how much more precise these machines can be in doing optical laser surgeries. They can create extreme high but focused powered laser beams. Particle accelerators not just in medicine but in nuclear physics. The extreme high amounts of energy can be contained within bombs. They can be used for telecommunication systems or governmental organizations and air forces, for a variety of different things. So I know for a fact that particle accelerators aren't just the future of physics, but there's a future of science. We have all these abstract ideas, time travel, tachyonic motion, tachyon particles. But particle accelerators aren't really that far from going to those abstract, unimaginable ideas. They're moving particles at nearly the speed of light. Particle accelerators have such a potential future because the quantum field overall is just beginning to get higher and just beginning to get recognized around the world. Imagine when quantum scientists, there's a huge number of people doing a quantum engineering degree. Imagine the new minds that the new scientists will have in this generation. Imagine the particle accelerators, the evolution of the particle accelerators, just the amount of amazing things that could be done with a powerful technology like this. I believe that particle accelerators are not just the future of physics, they're the future of everything. Everything science. Thank you for listening to my presentation.